Good morning, students. Mr. Carver here. Today we're going to start Chapter 5. First semester consisted of 3 chapters of differentiation. Chapter 4 started us with integration or anti-differentiation. Chapter 5 continues it. So we've had some basic formulas that you were introduced to for finding the antiderivative in Chapter 4. Now we're going to expand into other functions, and we're going to explore not only deriving them, but also integrating them. So they have broken up these sections into separate operations. For instance, 5.1 is the natural logarithmic functions, and we are going to be deriving them only. 5.2, we'll start to integrate them. So you're going to see a lot of differentiation and integration mixed up throughout the chapter. There is a ton of memorization. Please keep on top of it. All right, I'm not sure that you have noticed this, but we have not been able to integrate something that looked like that. Because if we were looking for, or utilizing rather, the power rule, this is really the antiderivative of x to the negative first dx. And if I follow the algorithm for finding that antiderivative, remember it is power plus 1 over power plus 1 plus c. This is a problem. This is an undefined function, so this does not work. So let's take a look at 1 over x, which looks something like this, if you recall. And remember that 1 over x dx is a derivative written in differential form. So what I'm looking for is the antiderivative of this. So this curve, black curve that you're looking at here, again, 1 over x, is f of x. What I'm looking for then is a sketch of the antiderivative of 1 over x. So again, if this is the derivative, remember this is the numeric value of the slope of the original. So if I label this up, remember the location of this curve gives me the slope of the original. So I'll do the original curve in red. And what I have here is, if I'm looking in quadrant 3 there, I've got a slope that's very close to 0 going to negative infinity. So if I draw it, remember it doesn't matter where I draw it, it looks something like this. Goes down to negative infinity. I'm drawing it there for a reason. I'll show you why in just a second. If I look at the black curve in Q1, that is f of x, looks like my slope goes from infinitely positive to a slope of a number that is approaching 0. So if I draw it in the right-hand side, it might look something like this. And I don't know if you recognize that curve, but the title of the chapter, or the section rather, gives it away. If I just look at, say, this portion right here, you might remember this or recognize that from pre-calculus. That is y is equal to the natural log of x. If I look at both sides, that's actually the natural log of the absolute value of x, which means if I integrate this, the integral of x to the negative 1 dx, what I get is the natural log of the absolute value of x plus c. Now, again, in 5.1, we're actually deriving natural logs, which means I'm going to start with this function, and I'm going to move in this direction. In 5.2, we start going the other way. So let's take a look at a few examples. Here's the first formula that you'll need to memorize. The derivative with respect to x, remember d over dx is a command telling you to derive what follows. The natural log of x, as you saw from the previous page, turns out to be 1 over x plus c. And remember, the c is a hedge. That's wrong. Completely wrong, so let's just disregard that. You get the plus c when you antiderive. It is just 1 over x. More broadly or more generally, if I take the derivative with respect to x of the natural log of u. Now, u is a differentiable function of x, and it stands for a function that is given in terms of x, but it's not solely x. So what I'm trying to do is express a chain rule derivative here, and it might make sense since we're driving with the chain rule. Remember, you derive the outermost function first, so the natural log of something is equal to 1 over what I'm natural logging, just like in the first line here. Right, the natural log of x is 1 over x. I think it makes sense then that the derivative of the natural log of u is 1 over u. But then I need to move inside, and if I'm keeping track of what I'm deriving, I've derived the natural log. Now I need to multiply this by the derivative of the innermost function. And by the way, the same holds true in line 1 here. If I take the natural log of x and I derive it, I get 1 over x, and I just multiply that by the derivative of the innermost function, which is times 1, which is why generally it's not written. All right, you need to memorize this formula. The derivative of the natural log of something is 1 over that something times the derivative of that something. All right, now, before I move on to examples of how to implement these formulas, we need to go back up here a little bit and just review some properties of natural logs. These properties should look familiar. I believe you did them last year in pre-calculus. You probably also saw them briefly in Algebra 2. The first property is, if I take the natural log of the number 1, what you get is 0. And by the way, here's why this is. If you recall the natural log of x, that is really the same as log base e of x, as opposed to just the log of x, which is log base 10 of x. So if you don't see a number, the assumption is that it is the common base, which is a base of 10. And if you have the natural log, the assumption is that it is log base e. Also, keep in mind that when you're working with logs, you can switch it from logarithmic to exponential form to more clearly see the property. For instance, if I have the natural log of 1 is equal to 0, remember this is log base e. To switch it from logarithmic to exponential, the base of the log comes over to the other side and bumps the exponent into the air. This gives me e to the 0. The natural log then disappears, and I'm left with 1 on the left-hand side. So e to the 0 is, in fact, 1. I should also mention that natural logs, or logs in general, are nothing more than exponents. So logs are exponents. They are the exponent that the base needs to give you this number right there. All right, let's continue. Second property is, if you're taking the natural log of a product, that is equal to the natural log of the first plus the natural log of the second. I should also mention that there is a property of natural logs that falls under this second property here, and it's this. Let me just remind you of this. If I take the natural log of e to the first, and I set this equal to something, let's call it x. Remember, this is log base e of e to the first. If I switch this into exponential form, that x is the exponent, because remember, logs are nothing more than the exponents, and then the log disappears. So x is equal to 1 since the bases match. So if the base of the log and the base of the exponential expression match, you can think of them as canceling. For instance, if you have the natural log of e to the 5th, again, that's because that is log base e, that gives you 5. And you can see that clearly if I switch it into exponential. I get e to the 5th is equal to e to the 5th, which is in fact a true statement. So let me get rid of this. So if, for instance, I have the natural log of e to the second, we already know that that is going to be 2, but I think you would agree that that is also the natural log of e times e, which is the natural log of e plus the natural log of e, and these are all both to the first, so that's 1 plus 1, and that does give me 2. So you can see that that property does hold true. The right is equal to the left. All right, then the third important property here is the natural log of a quotient that is equal to the natural log of the numerator minus the natural log of the denominator. And actually, the last one now, I've got the natural log of a to the nth power. n is just some constant, that is equal to then the natural log, or n rather, times the natural log of a. You can take this exponent and move it down to the front. And so I can show you examples of each of those quickly. The third one here, if you've got the natural log of e to the fifth over e to the third, that fraction there can be reduced to the natural log of e to the second. Two more on the top than I do on the bottom, which is equal to 2. I could also break this up to show you the right-hand side. E to the fifth divided by e to the third is equal to the natural log of e to the fifth minus the natural log of e to the third, which is 5 minus 3. That also gives you 2, so the right does match the left. And the last one there I think is easy to see as well. If you have the natural log of e to the fifth, that is equal to 5 times the natural log of e. Because you know this side is 5 and this side is 5 times 1, because that's e to the first. So again, the right does match the left. All right. So these four properties are going to be used extensively in this section. So now let's combine the properties and show you, and I'd like to show you how those properties apply to finding derivatives. All right, let's go back to the original formula. If I've got that y is equal to the natural log of x squared and I derive that, my y prime will be equal to, if you recall from a few pages back, when I derive the natural log, it is 1 over what I am logging times the derivative of what I'm logging. So this gives me 2x over x squared. The x's cancel. This gives me 2 over x. You can also use the property for the natural log, because we know that y equals the natural log of x squared can be written as y is equal to 2 times the natural log of x. So when I derive that, I have a constant multiple rule of 2 times the derivative of the natural log of x, which is 1 over what I'm logging, times the derivative of what I'm logging. So the properties allow you to cut to the chase and get to a reduced form right off the bat. You can see that this does equal to 2 over x without any cancellations. So you'll end up in the same spot. All right, likewise for more complex natural logs. Something like this, for example. You can already see the difficulty, right? If I'm natural logging this quotient here, and I want to derive that, first of all, it is 1 over what I'm logging times the derivative of what I'm logging. So if I just put 1 over what is inside the parentheses there, I begin this process with a complex fraction, which already makes it difficult to reduce. However, if I use the properties from 2 pages ago, I can say that y actually is equal to the natural log of the numerator minus the natural log of the denominator. I'm also going to change this into exponential form. I also know that the exponents sitting on the x, or what I'm logging, can be moved down to the front. So this can be simplified further by 2 times the natural log of x minus 1/2 the natural log of x squared plus 1. And now deriving is much, much easier than it was originally. My y prime will be equal to 2 times the derivative of the natural log of x, which is 1 over x times 1, minus, I've got my 1/2 constant multiple out to the front, times the derivative of the natural log of x squared plus 1, that is 1 over what I'm logging, times the derivative of what I'm logging. All right, these 2's can cancel. This gives me 2 over x minus x over x squared plus 1. That's probably enough simplification. In this section, this simplification becomes extraordinarily difficult. So at this stage in the game, I don't see a need to go any farther with this. You can just leave this as your answer. You would, of course, have to get a common denominator and combine it into a single fraction if I wanted you to simplify it. I will let you know. And now that I'm thinking of it, let's just go ahead and work through this quickly. I'm going to common denominator of x times x squared plus 1. Multiply this top and bottom by x, this top and bottom by x squared plus 1. And this is going to give me then 2x squared plus 2 minus x squared, all over my common denominator of x times x squared plus 1. Combine like terms. This gives me x squared plus 2 all over x times x squared plus 1. And that then is a simplified version. Whew, okay. All right. Here's another complex one. Let's go ahead and take a look at this. This y prime then is going to be equal to, remember I work outside in, the natural log of something is 1 over what I'm natural logging. And I'm going to keep track of this chain rule here. So now I go inside. I've got the tangent of 3x. That is the tangent of something. Remember, that is also chain rule because it's trig. So the tangent goes to the secant squared of that thing. Again, I'll keep track of what I'm derived here. So the tangent's now done. And now I go to the innermost function, and I multiply that all by 3. And for the majority of these, I'm just going to have you set these up. So that's it right there. All right, let's take a look at this one. Here's another chain within chain within chain. Let's just start with the outermost function first. That is this natural log right here. So I've got y prime is equal to 1 over what I'm logging. I'm logging the natural log of x squared plus 1 to the 1/2 power. So I'm done with that portion right there. I now go inside my outer set of absolute values. It's the natural log of, when I drive that, is 1 over what I'm logging on the inside. So now I'm done with that. And now I go inside. The next outermost function is the 1/2. That's 1/2 x squared plus 1 to the negative 1/2. Cross that off, and I multiply that all by 2x. All right, guys, that should be enough to get you through the homework tonight. Let me know if you have any questions, and I will see you soon. Thank you.